video, I will walk you through how to use tree diagrams to evaluate probability problems. The first step is to be able to create a tree diagram. And here's an example of a tree diagram. And please note, to start with, that in each of the examples we're looking at, we're going to say that each element in the sample space is equally likely. So in other words, when we see this tree where the first event is we flip a coin and we'll either have a head or a tail. And then the second event is that we roll a six-sided die and get 1, 2, 3, 4, 5, or 6. When I say that each item is equally likely, we're saying that getting a tail and then a 1 is one element here in the sample space, and that's equally likely to getting a tail and then a 6, and so on. So what happens is everything in our sample space is equally likely. Each item listed here in the sample space is just as likely to occur as anything else in that sample space. So if I wanted to calculate the probability of getting a heads on the coin and then getting an even number on the die, what I could do is I could look at the sample space and notice, first of all, how many elements are in the sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I knew that because there were 2 ways to flip a coin, 6 ways to roll the die, and 2 times 6 equals 12. So there should be 12 elements in the sample space. But of those 12 elements, how many of them have a head on the coin and an even number? It looks like there's a total of 3 elements in the sample space. So our denominator would be 12 because there's 12 possible elements to select from the sample space. And then our favorable outcome is a head on the coin with an even number on the die. So looks like that's 3 out of 12. We do need to be able to reduce the 3/12 into lowest terms. And to do this, I notice that 3 goes into 3 and also into 12. So it's 1 out of 4. If I were to divide 1 divided by 4, I'd get 25 hundredths, which translates to 25%. So there's a 25% chance that if you flip a coin and then roll a six-sided die, that you're going to get a heads on the coin and an even number. What's the probability of getting a tail on the coin and then a number that's less than 3? A number that's less than 3 would only be a 1 or a 2. A 1 or a 2 are the only 2 numbers less than 3. So it looks like out of our sample space of 12 total elements, there are 2 that are favorable, where there's both a tail and a number less than 3. When I reduce this, I get 1 over 6. And when I divide 1 divided by 6, I get 0.16 repeating. So if I round it to the nearest thousandth, I could call this approximately 16 7/10%, or approximately 16.7%. Let's talk just a little bit more about how the tree is created. We start with the first outcome, so an H or a T. So I draw 2 lines, one to H, one to T, and then from each of those first outcomes, since the second event has 6 outcomes, I draw 6 lines from there, and then number 1, 2, 3, 4, 5, 6. And then the sample space is a list of all the outcomes that are combined. So heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, and so on. Gives us a list of the sample space. Let's look at another example with this flipping a coin and then rolling a die. What's the probability of getting a head and a 6? Notice that that only happens one time out of all 12. Out of all 12 elements in the sample space, only one of them has a head and a 6. When I divide this, I get 0.08 and then a 3 repeating. So I could call this 8.3%. Another example, what's the probability of getting a tail and a number that's greater than 2? It looks like that would be a 3, 4, 5, or 6. There's 4 of those in our sample space. 4 out of 12 reduces by 4 to 1/3. If I divide 1 divided by 3, I'm going to get 3 repeating. So as a percent, if I multiply by 100, I'd get 33.33%, or 33.3%. Let's try another example. An example where we're going to choose 2 winners. We have 4 contestants, Charizard, Mela, Lou, and Paula. And of these 4 possible winners, we're going to choose 2 winners. What's the probability that Charizard is one of the winners? Well, to be one of the winners, that means that Charizard could be the first winner or the second winner. So it looks like there's 1, 2, 3 cases where Charizard is the first winner. If we continue, we get 4, 5, 6 total combinations where Charizard is one of the winners. And if I look at how many names there are for the first selection, there's 4, and then 3 more for the second. So it looks like the denominator is 12 again. There's 12 items total. So it looks like Charizard's chance of being one of the 2 winners is 1/2. If you divide 1 by 2, you'd get 0.5. So we could write that as 50%. Let's talk just a little bit more about how this tree was created and why there are 12 elements in the sample space. Notice that once Charizard is selected, he can't be selected again. So although the first selection has 4 options, the second selection, the only ones left are Mela, Lou, and Paula. So there are only 3 choices for the second selection. So that gives us a total of 12 elements in the sample space. We could think of this as drawing, where we draw a name from the hat, and then we do not replace the name. So since we don't put Charizard's name back, we can't choose him on the second draw. That's why it's not 4 choices on the second draw. So what's the probability that Mel and Paula both win? Probability that they both win could happen either with Mel being chosen first and then Paula, or Paula being chosen first and then Mel. So it looks like there's a total of 2 out of the 12, which is 1/6. And as we found earlier, when we divide 1 divided by 6, we get 1/6 with the 6 repeating. So if I round that to 3 decimal places, I'd get 16.7%. Let's look at the probability of either Lou or Paula winning. The probability that at least one wins. Notice that it's assumed that if they both win, so where do we have Lou and Paula both winning? Lou and Paula both winning here. Lou and Paula both winning here. Notice that those are also included. But altogether, that gives me all but 2 of them. So 10 out of the 12. So there's a pretty good chance that if Lou and Paula are brother and sister, that someone from their family will win, right? 10 and 12 chance. If we reduce that, 2 goes into 10, 5 times 2 goes into 12, 6 times. So 5 out of 6. If I do 5 divided by 6, I get 0.83 repeating. So 83.3% chance that at least one of them will win. And then notice that if I wanted to calculate the probability that neither of them win, that just leaves these 2 other outcomes in the sample space. That's where Charizard and then Mela win, or Mela and then Charizard. So I could say, I could count them up and say that that's 2 out of 12, which is 1 in 6. But notice that this 5, 6, the probability that Lou or Paula win, this 5 over 6, added to the 1/6 gives us the entire sample space. So what we get when we add the entire sample space is 1 whole. Notice that when we add up everything in the sample space, the probability of anything happening, there's 100% chance that one of these 12 things will occur. When we add the different probabilities, if they include everything, so we've got Lou or Paula winning, and then neither Lou nor Paula winning, that's got to add up to a total of 1. What's the probability in this case that we get macaroni salad and a Sprite? So what's happened is we have a menu where you could get a roast beef sandwich, ham sandwich, or turkey sandwich, and then macaroni or potato salad, and then Coke or Sprite. So what's the probability of having macaroni and Sprite? It looks like there's 3 of the options. And how many options are there all together? Well, there's 3 ways to select a sandwich. There's 2 salads to choose from, 2 soft drinks to choose from. So it looks like the total number of outcomes in the sample space is 12 again. So we find how many ways could we do each event, multiply that to get the total number of elements in the sample space. There's 12 elements in the sample space. 3 of those elements include a macaroni and Sprite. So 3 and 12, or 1/4, which 3 and 12, 1/4, 1 divided by 4 gives us 25 hundredths. Multiply by 100 to get 25%. On the same menu, what's the probability of getting roast beef and macaroni? Looks like 2 elements in the sample space out of the 12, or 1/6. You should be able to convert that to a decimal and a percent. How about turkey sandwich and Sprite? That could be turkey and sandwich, macaroni and Sprite, or turkey sandwich, potato salad and Sprite, but 2 out of the 12, so 1 in 6 again. Let's look at another case. How many of the elements in the sample space have macaroni and Coke and do not have roast beef. So we have someone who likes macaroni and Coke, hoping to get macaroni and Coke, but doesn't want roast beef. Their chance of that happening is 2 in 12 because there's 2 elements that include both macaroni and Coke, but not roast beef. How about drawing some marbles? In this draw, what's going to happen is we're going to replace the marble. So you could think about it as you reach in and grab 2 marbles at the same time. The number of elements in the sample space, there's 4 ways to get the first marble. You know, I've got to go back. I think I misspoke that. Two marbles, they can't be selected at the same time. We've got to select one, put it back, and then select another. So you can't just reach in and get 2 marbles at the same time. What we're going to do with this one is we're going to replace them. So this will be with replacement. So we draw our marble. There's 4 different marbles we could get. Put that back, draw again. So do you see that there's a total of 16 elements in the sample space? 4 times 4, or 16. The number of sample points in the sample space is 4 times 4, or 16. And what's the probability that we get exactly 1 red marble? If we count up everything that includes exactly 1 red, there's 1, 2, 3, 4, 5, 6 out of the 16. I can reduce the 6 and the 16 by 2. 2 goes into 6 3 times. 2 goes into 16 8 times. And if I divide 3 divided by 8, I get 0.375, or 37.5%. There's a 37.5% chance that we get exactly 1 red marble.